Hey everyone, and welcome back to the Deep Dive.
Great to be here.
Ever played one of those brilliant physics puzzle games? You know, the ones that feel just incredibly satisfying when you finally figure out those clever mechanics.
Oh, yeah, absolutely. Where one small action sets off this whole amazing chain reaction.
Exactly. And you sit back and just go, I got it.
That's the feeling.
Well, today, we're not just playing them, we're actually diving headfirst into how you can make them.
That's the plan.
Our mission for this deep dive is to give you a complete practical primer. We want to show you how to bring those physics-based puzzles to life using Construct 3.
Which is a fantastic tool for this, by the way.
Yeah, it looks like a great no-code engine. Think of this as your shortcut to building those really engaging interactive experiences right from your web browser.
Great.
We're going to try and cover everything you need to know. You know, from setting up your digital canvas all the way to mastering some pretty complex interactions.
And that's really what makes Construct 3 such a game changer for aspiring creators, isn't it?
It seems like it.
It's this incredibly powerful tool, but it's also remarkably approachable. It's designed to empower your creative vision without you having to write, a single line of traditional code.
No coding at all?
Pretty much. Which means if you have an idea for a puzzle, you can focus entirely on the design, the mechanics, those satisfying aha moments.
Instead of wrestling with semicolons and brackets.
Exactly. Rather than getting bogged down in syntax, it really does lower the barrier to entry, inviting a whole new wave of potential game developers to jump right in.
Okay, so let's unpack this. Our journey begins with getting to know our workbench. Construct 3. Now, when I first heard no-code game engine, I admit I was a bit skeptical.
That's fair.
Is it genuinely as intuitive as it sounds? Or is there, like, a hidden learning curve we should know about? What exactly is it, and why is it such a big deal for someone maybe new to game dev?
That's a really good question, and it gets right to the heart of what Construct 3 is all about. At its core, it's an HTML5-based 2D game development engine.
Okay, HTML5, so web-based.
Exactly. And its design philosophy is, pretty revolutionary because it's meticulously crafted for creating games without any traditional programming code.
Right.
No C++, no Python, no complex syntax errors you have to fight with on a command line. You literally drag and drop elements, connect them visually, and define how they behave.
Drag and drop logic.
Essentially, yes. That intuitive visual interface is precisely what makes it exceptionally beginner-friendly. But, and this is important, don't let that ease of use fool you.
It's still powerful.
Absolutely.
Right.
It's robust enough that professional studios and indie developers use it to create and publish commercial titles. You see Construct 3 games on Steam, mobile app stores, even the Nintendo Switch.
Wow. Okay, so the no-code part is genuinely true then.
Yeah.
And you mentioned it runs in a web browser. That sounds incredibly accessible.
It really is.
Does that mean no hefty installations or complicated configurations?
Well,
like just open Chrome and go?
Exactly. That's one of its most powerful benefits. You don't need to download gigabytes of software or worry about complex setups. Construct 3 runs directly in your web browser.
Google Chrome is best, you said.
Chrome is generally recommended for optimal performance, yeah, but most modern browsers work just fine. And this means you can access your projects from, virtually any device with an internet connection.
So I could work on it anywhere.
Pretty much. Imagine working on your game on a school Chromebook, then picking it up seamlessly on your desktop at home, or even making quick tweaks on a tablet while you're, out and about.
That's amazing flexibility.
It fosters incredible adaptability. Think about different learning environments or remote collaboration or just capturing those spontaneous bursts of creativity whenever inspiration strikes.
It definitely lowers the barrier to entry.
Significantly. It empowers a much wider range of creators to bring their ideas to life.
That's fascinating. But how does it actually understand what you want the game to do without all that traditional code? If it's not lines of C++ or whatever, what's the fundamental logic?
That's where its foundational event-based system comes into play. Think of it as Construct 3's unique language. It operates on a simple yet incredibly powerful if this then that logic framework.
If this, then that.
Okay. Instead of writing code, you visually define game behavior by setting up events. Each event has two main components.
Right.
First, you have conditions. This is the if part of your logic.
Like if the player hits the jump button.
Exactly. Or if a physics ball collides with a wooden plank, you're defining the specific circumstances that need to be met for something to happen.
Got it. And the second part?
Second, you have actions. This is the then part. It's what executes when those conditions are true.
So they make the player jump.
Precisely. Or if the physics ball collides with the plank, the action could be apply an impulse to the plank or
Oh.
maybe destroy the plank and add 1 to the score.
Ah, I see. It's all visual cause and effect.
Exactly. And this visual, intuitive approach is a major relief for beginners because it completely eliminates those common syntax errors.
Oh, the bane of every programmer's existence.
Right, those notorious roadblocks in traditional programming. You're freed from wrestling with semicolons or curly braces and can instead focus entirely on the game's design, its mechanics, how the puzzle pieces fit together. It's truly like building with digital Lego bricks.
I like that analogy. Each brick is a condition or an action. That makes a lot of sense. So with this powerful tool, how do we actually begin building our first 2D scene, our digital canvas in Construct 3? What are the very first steps?
Okay, so once you've launched Construct 3 in your web browser, the very first step is simple. Select New Project.
Okay.
A dialog box will pop up asking you to define some initial settings for your game. Now, for a full-screen experience that looks good on most modern monitors, a good starting point for your game size is 1080p landscape.
1920 by 1080 pixels.
That's the one. 1920 wide by 1080 high. It provides a common aspect ratio and resolution, gives you plenty of space to design your levels.
Makes sense.
Now, while you start with this, it's a good habit to keep in mind, down the line, you'll want to think about making your game responsive.
Responsive, meaning it adapts to different screens.
Exactly. Adapting gracefully to different screen sizes and orientations, especially if you're thinking about mobile devices. But for now, 1080p is a really solid foundation to build on.
Okay. And once we're in, the interface can feel a bit busy at first glance.
Yeah.
What are the absolute main parts we should get familiar with, our sort of core command center?
Absolutely. Navigating the interface effectively is key. Think of it like your game development studio with different specialized workstations.
Cool.
First, front and center, you have the layout view. This is your main design area, the visual canvas where your game levels come to life.
Where you place all this stuff.
Yeah, exactly. You'll spend a lot of time here visually placing and arranging all your game objects. Characters, platforms, puzzle elements, backgrounds, everything. It's basically what the player sees.
Got it. The main stage.
Then, typically over on the right side, is the project bar. Think of this as your project's table of contents. Or maybe it's nerve center.
Right.
It displays a list, sort of a hierarchy, of all your game assets, your objects, your crucial event sheets. From here, you can easily jump between different parts of your game, manage assets, organize everything.
So if I need my bouncing ball object, I look there.
That's where you'll find it. Or your level 1 event sheet, it's all listed there.
Okay, project bar on the right. What about the left?
On the left, you'll usually find the Properties bar. Now, this is a dynamic panel. Its content changes based on what you've selected.
Ah, context sensitive.
Exactly. Whenever you click on an object in your layout or a behavior or an effect, this bar instantly fills up with specific settings and configurable properties for whatever you selected.
Like changing the size or color.
Precisely. Select your player. You can adjust its size, initial position, animation speed right there. Select a background. Maybe set its tiling properties or opacity. It's your quick access panel for all those object attributes.
Cool. Layout view, project bar, properties bar. Anything else major?
Yes. Crucially for 2D game design, there's the layers bar. This is a super powerful tool for organizing your game elements into different visual planes.
Like those transparent sheets you mentioned.
Exactly, like snacking transparent sheets of acetate. This is absolutely essential for managing depth and visibility in a 2D world.
So putting the background behind the player.
Exactly. You might have a background layer for scenery, a gameplay layer for characters and interactive puzzle bits, a HUD layer for scores or health bars.
Making sure the score stays on top.
Right, ensuring they always appear on top of everything else. You could even have a pause menu layer that pops up over everything when the game is suspended. It not only makes your project immensely cleaner and easier to manage, but also dictates that crucial visual drawing order.
Okay, so layouts are like the different levels or screens, and layers organize things within a screen, controlling what's on top of what. Did I get that right?
Precisely. You nailed it. Think of layouts as entirely distinct screens or levels. You'll have your main game layout, sure, but then separate layouts for your main menu, option screen, level select, maybe a game over screen.
Keeps things tidy.
Incredibly beneficial for project organization. It lets you manage different game states independently. When you go from the main menu to level 1, you're essentially just telling Construct to jump from the main menu layout to the level 1 layout. Makes development cleaner, more efficient, easier to debug.
Makes sense.
And regarding those layers, they also have that cool trick beyond just drawing order. Z elevation.
Z elevation, like depth.
Kind of. Imagine a painting where some things seem to pop out a bit. Z elevation lets you subtly shift objects within the same layer, or even whole layers, forward or backward, on a kind of virtual depth axis.
Ah, for like a 2.5D look.
Exactly. Fantastic for creating that sense of 2.5D. Platforms might feel slightly in front of or behind each other, or you can add subtle parallax effects to your background without needing tons of separate layers. It's a great tool for adding visual polish and an immersive feel.
All right, now that we understand our environment, let's talk about the real core of a physics puzzle game, making things move and interact realistically. This is where Construct 3's built-in physics behavior comes in, right?
Exactly. This is where it gets really interesting for building those dynamic, almost Rube Goldberg-style contraptions.
Yeah.
The physics behavior is the magic ingredient. It truly brings your game elements to life with realistic movement. And what's powering this behavior in Construct 3 is the industry-standard Box 2D physics engine.
Box 2D? I think I've heard of that.
You probably have. It's a renowned 2D physics engine, specifically designed to simulate rigid body dynamics.
Rigid body dynamics, meaning solid objects interact.
Precisely. It handles how solid objects interact with forces, gravity, and each other. It allows for those highly dynamic and interactive elements in your game world. Now, Construct 3 also has a powerful 3D physics engine. But for our 2D physics puzzles today, Box 2D is the workhorse doing the heavy lifting behind the scenes.
Okay, so how do we add this magic Box 2D behavior to, say, a ball or a plank?
It's remarkably straightforward. First, you just select the object you want to apply physics to in your layout. Maybe it's that wooden plank for your lever or the ball you're going to drop.
Okay, click on the object.
Then you head over to its properties bar on the left, click on behaviors, then add new behavior, and finally choose physics from the list that pops up.
That's it?
That's basically it. Once added, any instance of that object type automatically becomes a physics object. It's ready to interact with your game's simulated physical world. It'll react to gravity, bounce off other physics objects, respond to forces you apply, the works.
So once you add that physics behavior, a whole suite of new properties appears in the properties bar for that object. These look like the crucial controls for how the object actually behaves in the physics world.
Exactly right.
This seems like the key part for really fine-tuning our puzzle mechanics. Can we dive into some of the most critical ones? Not just what they do, but maybe why they matter for puzzle design.
Absolutely. These properties are your toolkit for sculpting realism and, more importantly, designing how your puzzles function.
Okay, what's first?
First up, and this one is huge, is immovable. This property is absolutely paramount for anything that needs to stay put. Think floors, walls, static platforms, the pivot point of your lever.
Things that shouldn't get pushed around.
Exactly. When you enable immovable, it effectively tells the physics engine this object has infinite mass. It prevents it from being affected by gravity or any forces from other physics objects. Crucial for creating a stable environment.
Makes sense.
Now, here's a critical rule, and honestly, it's a common pitfall for beginners. I call it the physics with physics rule.
Physics with physics.
Yeah. Physics objects only interact realistically with other physics objects. This isn't just a setting, it's fundamental to how Box 2D creates its own little simulated world inside your game.
What does that mean in practice?
It means if you have a floor object and you only give it the standard solid behavior, which is great for traditional platformer collisions, by the way,
Right.
a ball with the physics behavior enabled will just pass right through it. Poof. Gone.
Wait, really? Even if the floor looks solid?
Yes, because for the physics engine, that floor doesn't exist in its world unless it also has the physics behavior. So for your physics ball to collide with your floor, that floor must have the physics behavior applied, and you need to set its immovable property to true.
Ah, okay. That's a big one. The floor needs physics too, just immovable physics.
Exactly. Understanding that separation between the visual look and the physical simulation is often the first big aha moment for new physics game devs. Suddenly, lots of weird glitches make sense.
Good to know. What's next?
Right.
Collision mask.
Right, the collision mask. This property dictates the actual shape the physics engine uses for collision detection. It's what the engine sees when objects interact. This impacts both how accurate your collisions are and, potentially, your game's performance.
So it's not always the visual shape.
Not necessarily. You have a few vital options here. First, use collision polygon.
Mm-hmm.
This uses a custom polygon shape that you actually define yourself in Construct's animations editor. It offers the most precise collisions, perfect for irregularly shaped objects like maybe a star-shaped puzzle piece or a complex lever.
So you can trace the exact shape.
You can. But a pro tip, try to keep these polygons relatively simple. Overly complex ones with hundreds of points can start to impact performance. Simpler is generally better if you can manage it.
Gotcha. What else?
Second option, bounding box. This is the simplest. It just treats the object as a plain rectangle for collision purposes, completely ignoring any custom polygon you might have drawn.
So just the outer edges.
Yep. Often the most performant choice for simple rectangular shapes like blocks, planks, walls. If it's basically a rectangle, use bounding box.
Okay. And the last one.
Third is circle. This makes the object behave as a perfect circle for collisions, ideal for anything that needs to roll smoothly, balls, barrels, gears. Choose this when that perfectly round collision is essential for your puzzle mechanic.
That makes sense. Polygon for custom shapes, bounding box for rectangles, circle for round things.
You got it. Then there's prevent rotation. If you enable this, it stops the object from spinning or rotating due to physics collisions.
Oh, useful for player characters, so they don't tumble wildly.
Exactly. Highly useful for main characters and platformers where uncontrolled spinning would feel awful. Or for puzzle objects you want to stay upright, even if they get hit. But remember, this only stops physics-induced rotation. You can still rotate it deliberately with other actions if you need to.
Okay, what about weight? Density.
Density. This determines how heavy the object feels and how hard it is to push or accelerate. Think of density like, well, how much stuff you've packed into a certain size box.
Feathers versus lead.
Perfect analogy. Same size box, different weight. In Construct, the object's actual mass is calculated by multiplying its density value by the area of its collision mask. Higher density means more mass.
So harder to move.
Harder to accelerate, harder to decelerate. Only the relative values matter here, though. A density of 6 is simply twice as dense as 3. So for a puzzle, maybe your cannonball has a high density, but the little wooden block it needs to knock over has a low density.
Got it. Friction. That sounds important for puzzles.
Crucial. Friction controls how much an object slows down when it's sliding against another physics object. A value of 0 means no friction at all, like sliding on perfectly smooth ice.
Slides forever.
Pretty much. A value of 1 means maximum friction, like dragging a brick on rough concrete. It stops very quickly. This is key for slopes or objects that need to slide into a specific spot and then stop.
Okay. And bounciness. Elasticity?
Right, elasticity, often called bounciness, or technically restitution. It dictates how much an object bounces upon collision. A value of 0 means no bounce at all, like a rock hitting the ground. Thud.
Or a beanbag.
Good one, yeah. A value of 1 means maximum bounce, like a super rubber ball that practically returns to its original height. For a puzzle, your main bouncing ball might have high elasticity, but the target it needs to hit might have 0, so it stays put once activated.
Nice. What about damping? Linear and angular. Sounds complex.
They sound complex, but the concept is simple. Linear damping simulates resistance, like air resistance or maybe friction with the air. It causes straight-line movement to gradually slow down over time.
So things don't move forever unless you want them to.
Exactly. A value of 0 means perpetual motion, like in space. Higher values mean faster deceleration, good for making things feel more natural, like they eventually come to rest.
And angular damping.
Same idea, but for spin. Angular damping affects the object's rotation. A higher value will make a spinning object gradually stop spinning. Low angular damping lets a gear keep spinning for a while. High damping stops a tumbling character quickly.
Got it. Damping slows things down, linear for movement, angular for spin. Was bullet. Sounds fast.
It is for fast things. The bullet property is a specific performance optimization. It's designed for very fast-moving objects, like projectiles from a powerful catapult or, well, bullets.
What's the problem with fast objects?
Sometimes, if an object is moving extremely quickly, it might tunnel straight through another object without the physics engine noticing.
Like it's there one frame and pass to the next.
Exactly. It moves so far between frames that the collision check misses it entirely. Enabling bullet forces the engine to perform extra, more accurate collision checks for that object, preventing this tunneling effect.
Ah, but it costs more performance.
It does consume more processing power, yes. So you should use it sparingly. Only on those truly high-speed objects where tunneling is actually a problem. Don't just turn it on for everything.
Okay, good tip. And finally, enabled. Seems obvious.
Yeah, enabled is just a simple toggle. On or off. It activates or deactivates the physics simulation for that specific object. If it's disabled, other physics objects will just pass right through it, ignoring it completely in the physics world. Useful for temporarily switching off a puzzle element, maybe.
That's an incredible amount of fine-tuning available for each object.
Yeah.
But okay, once we have our objects set up with their properties, how do we actually control them dynamically? Like in response to player input or other events in our puzzle. I imagine just manually setting their X and Y position like you would a normal sprite might cause chaos with the physics engine.
You're absolutely right to be wary of that. That's a huge don't. It's highly, highly recommended to control physics objects only through the physics behavior's own dedicated actions.
Not the standard set position actions.
Definitely not. Manually changing a physics object's position using standard set X or set Y actions is essentially teleporting it. This can lead to really unrealistic, unpredictable behavior. The engine tries to compensate for that sudden non-physical movement, and you get jittering, crazy bounces, objects falling through floors. It's messy.
Okay, so use the physics actions. What are the main ways to control them then?
Let's look at the primary methods for dynamic physics-compliant control. First up, forces.
Forces, like pushing.
Exactly. A force is a continuous influence that causes an object to accelerate over time. Think of it like constantly pushing something with a steady hand. You have a few actions here.
Okay.
Apply force lets you specify an X and Y component, pushing it horizontally and vertically. Apply force at angle lets you give it a specific strength and a direction and angle to push. And apply force towards position pushes it with a set strength towards a target point.
So you can push things around continuously.
Yes. And crucially, if you apply a force away from an object's center of mass, which is usually its default origin point, image point 0, it will also cause it to rotate. Adds nice dynamic movement.
Ah, applying force off-center makes it spin. Cool.
For your puzzle, you might apply a continuous force from a fan object to gently push a ball along a specific path.
Okay, forces are continuous pushes. What else? Impulses.
Right, impulses. An impulse is different. It's a sudden one-off impact, like hitting a ball with a bat or the burst from a small explosion.
A quick kick.
Exactly. You'll typically use actions like apply impulse at angle, and apply impulse towards position. These are for instantaneous effects.
When would you use those?
They're perfect for trigger events. Like on collision with another object, you might want an immediate reaction. When your dropped ball hits the lever, boom, apply an impulse to the catapult arm to launch something else.
Makes sense. One-time hit.
And just like forces, applying an impulse off-center, maybe near an object's edge, is much more likely to make it spin. That could even be part of your puzzle mechanic.
Okay, forces and impulses. What about rotation specifically?
For that, you have torque. Torque is specifically a rotational force. It causes an object to spin faster or slower around its own axis.
Like twisting something.
Precisely. You can use apply torque towards angle, and apply torque towards position actions to apply rotational acceleration. If you want a wheel to spin up or a seesaw to tilt quickly, torque is the action you want.
Got it. Can you just set the speed directly?
You can. For direct control of speed, there are set velocity and set angular velocity.
Velocity. That's speed and direction, right?
Yep. These actions let you directly set the linear speed of a physics object in pixels per second or its rotational speed in degrees per second.
But isn't that like setting the position?
Yeah.
Bad.
It's different. While they directly control speed, they still operate within the physics engine's framework. The engine understands you're setting its current velocity, not just yanking it to a new spot, so it's generally safer than set position. You might use set velocity to give a launched object a very precise initial speed, overriding any previous forces at that moment.
Okay. So that's generally okay to use.
Yes, much better than set position. And finally, if you absolutely must instantly reposition an object, but you want it to keep its current momentum,
Like a portal.
exactly like a portal, there's this teleport action. This is a special case. It instantly moves the object to a new location without affecting its current physics velocity. Perfect for portals, or maybe resetting a puzzle piece back to its start without killing its spin or movement if that's intended. Use it carefully, though.
So we can push and hit things, make them spin, give them sudden boosts. But what about the most fundamental force, the one pulling everything down? Gravity. How does Construct 3 handle that basic downward pull, and can we mess with it for our puzzles?
Good question. By default, yes. All physics objects you create in Construct 3 are affected by gravity. It's just there, a constant invisible force pulling everything downward.
Towards the bottom of the screen.
Right. In Construct's coordinate system, the y-axis number increases as you go down the screen, so gravity naturally causes objects to accelerate downwards, just like you'd expect in the real world. It's on by default.
But can we change it? Like make a level on the moon? Or in space?
Absolutely. You're not stuck with just one universal gravity setting. Construct 3 gives you control over this global force. You can use the Set World Gravity action.
Set world gravity, okay.
This action lets you adjust the strength of that downward pull.
Yeah.
Or you can even turn it off entirely.
Gravity off, so things just float.
Exactly. If you're making a space-themed game where objects should just drift endlessly unless pushed, you'd set the world gravity to 0.
Cool. And for the moon?
For a moon-level feel, you could set gravity to a much lower value than the default. Jumps would be higher, falls would be slower, things would feel lighter.
And you could make it stronger, too, like Jupiter gravity.
You could. For a super heavy, dense world feel, you could significantly increase the gravity value. Things would fall fast and hit hard. This action affects all physics objects in your game's world, well, within that layout, technically. It gives you this overarching control over the fundamental physics environment.
That opens up some crazy puzzle ideas where maybe gravity changes mid-level.
Precisely. Gravity itself can become a variable, a core part of the puzzle mechanic.
Okay, so we've got the physics down for individual objects and the world. Now, what does this all mean for actually structuring our puzzle game? Making things happen in an organized way. You mentioned graphic layers earlier, those transparent sheets. How do they really help organize the visuals, and then how do we build the logic that ties it all together?
That analogy of transparent sheets is perfect because it really gets to the core of what layers do, and mastering them is critical for any robust game, especially a potentially complex physics puzzle. They serve multiple vital purposes.
Okay, lay it on me. Why are layers so important?
Well, first, just pure organization and structure. Imagine hundreds of game objects, backgrounds, characters, UI bits, puzzle pieces, all just dumped together on one single plane.
Chaos.
Yeah.
Utter chaos.
It would be a nightmare to manage. Layers help you logically group everything, like we touched on. A background layer for static stuff, a gameplay layer for all your interactive characters, and puzzle bits, the ball, the lever, the target, maybe a foreground layer for things that pass in front, a HUD layer for score, timer.
Keeping the interface elements separate.
Right. And making sure they always appear on top.
Wow.
This structured approach just makes your project significantly cleaner, much easier to navigate, especially as your game gets more complex. Good organization saves huge amounts of time and headaches later.
Okay, organization. What else? You mentioned drawing order.
Yes. Second, layers inherently manage drawing order, often called Z-order. Objects on a higher layer in the layers bar are always drawn on top of objects on a lower layer. Period.
Simple enough.
Higher up the list, further forward it appears. Exactly. Crucial for visual depth and making sure your game looks correct, your player on the gameplay layer needs to be in front of the scenery on the background layer. If a puzzle piece needs to visually pass behind a foreground pillar, you just make sure that pillar is on a layer above the puzzle pieces layer. It controls the whole visual hierarchy.
Makes sense. What else do layers do?
Third, they're great for visual effects and batching. You can apply effects like shaders, color filters, blur effects to an entire layer at once instead of having to apply it individually to every single object on that layer.
Oh, that's efficient. Apply a rain effect to the whole foreground layer.
Exactly. Great for efficiency and consistent styling. And related to that is rendering optimization through batching. If configured correctly, Construct 3 can draw all the objects on a single layer in one batch call to the graphics card. GPU. This significantly improves performance, especially if you have lots of sprites.
Batching sounds technical, but good for speed.
It is, and this leads to that important performance note we touched on earlier regarding render cells.
Right, the snapshot thing. Good for static layers.
Fantastic for static layers, yes. Enabling render cells on a layer tells Construct to take a static picture of that whole layer and just draw that one picture. Huge performance boost for static backgrounds or UI.
But terrible for moving things.
Absolutely terrible.
Yeah.
Never enable render cells on layers with moving objects, animated sprites, or particles, because if anything changes on that snapshotted layer, the engine has to constantly retake the picture every single frame, which ironically creates more work and kills performance. So, powerful tool, but use it wisely, static elements only.
Got it. Static layers good, dynamic layers bad for render cells. Any other uses for layers?
Fourth, they are excellent for game state management and transitions. Super useful for managing different game states visually, like when you pause the game.
Yeah.
You can simply make your gameplay layer invisible, or maybe semi-transparent, and then make your pause menu layer visible. Instant visual change, clean and easy, no need to destroy and recreate everything.
Just toggle visibility.
Yep. And you can also control the opacity of entire layers. This allows for smooth fade-in and fade-out transitions for whole sections of your game, fading from a level complete message back to the main menu, for example. Really slick.
Okay, so layers keep our visual house in order. Essential stuff. But how do we actually make anything happen? You called the event sheet the brain of the game before. Can you walk us through how this visual scripting system, this no-code if this then that thing, really works to build out potentially complex game logic?
Absolutely. The event sheet is the brain, the central nervous system. It's where you define all the rules, all the behaviors, all the logic of your game using Construct's visual scripting system. And like we said, it completely bypasses traditional coding syntax, which makes even pretty complex logic surprisingly approachable.
So remind me the two main parts, conditions and actions.
Exactly. First, conditions, the if part, the trigger. If the player presses space, if the physics ball collides with the lever, if the score variable is greater than 100, you set up the precise circumstances that must be true.
Okay, the trigger.
Second, actions, the then part. What executes when those conditions are met? Then make the player's sprite jump. Then apply impulse to the catapult arm and play a thwack sound. Then go to the level complete layout.
Cause and effect, visually laid out.
Precisely. The beauty is, it feels like solving a puzzle itself sometimes. You connect the logical pieces directly. And as mentioned, no syntax errors. That's a huge relief for beginners.
Wow.
Makes complex logic way less frustrating.
But as games get bigger, I imagine these event sheets could get huge and messy.
They certainly can if you're not careful. That's why organization within the event sheet itself is paramount. You can use groups and sub-events.
Like folders.
Exactly like folders within folders. You create a hierarchical structure. You might make an input handling group, an enemy AI group, a puzzle mechanics group. Inside puzzle mechanics, you could have sub-events for lever activated, target hit, reset puzzle.
Keeps related logic together.
Makes your sheets cleaner, easier to read, much simpler to manage and debug, especially when you might have hundreds of events.
Okay, groups are good. Anything else for complex stuff?
Yes, you can also create functions. These are incredibly useful. They're reusable blocks of events. Think of them like mini programs you build once, give a name, and then you can call that function whenever you need that block of logic executed.
Like a shortcut.
Kind of. For example, you could make a function called reset level. Inside it, you put all the actions needed to move puzzle pieces back to start, reset the score, clear forces, whatever. Then, instead of copying all those actions everywhere you need a reset, you just call the reset level function.
Saves a ton of time and avoids mistakes.
Tremendous amount of time, keeps sheets clean, avoids redundant logic. Functions are your friend for complex projects.
And what about storing data? Like the score, or maybe whether a switch is flipped?
For that, you'll rely heavily on variables. Variables are like little containers that hold different kinds of information.
Numbers, text.
Yep. They can be global, meaning accessible from anywhere in your game, perfect for things like player score or current level. Or they can be local, meaning they only exist within a specific scope, like inside a single event or function, useful for temporary calculations.
Right.
They can store numbers, scores, counts, physics values, text, player names, messages, or Booleans, which are just true-false values, like is game paused, true-false, or has puzzle been solved, true-false.
How would variables help in a physics puzzle specifically?
Oh, tons of ways. You could use a variable to track how many times a physics block has bounced before it triggers something, or count how many pieces are correctly placed, or maybe store the remaining force available in some puzzle mechanism that depletes over time. Variables are the unsung heroes that make your game dynamic, reactive, and allow for complex state tracking.
Okay, this is all clicking together now. We set up objects with physics properties, organize visuals with layers, and build logic with events, conditions, actions, groups, functions, and variables. Phew.
It's a powerful combination.
We briefly touched on collision masks way back in the physics section, but now that we understand event sheets, how does the actual detection of those physical interactions become that powerful trigger for gameplay logic?
Yeah.
This feels like the absolute core of a physics puzzle game.
It absolutely is the core. This is where the physics simulation directly connects to your game's rules and progression. That on collision with another object condition, you'll be using that constantly in your event sheet to drive your puzzle
The
mechanics.
main trigger.
Definitely one of the main ones.
Hmm.
And remember how we talked about the collision mask property for each physics object, polygon, bounding box, or circle?
Yeah, the shape the engine sees.
Exactly. That property precisely dictates what the physics engine considers a collision. And that precise seeing is what triggers that specific on-collision event. If your ball's collision mask physically touches your lever's collision mask in the simulation, boom, that event fires, and whatever actions you link to it will run.
So the physics interaction directly runs my event logic.
Precisely. This is where the real magic happens for physics puzzles. Collisions become your primary input method for puzzle mechanics. For example,
Like what?
well, a physics block colliding with a specific target zone could trigger a chain reaction, open a door, activate another machine, maybe start a domino run.
Okay.
Or a rolling ball hitting a pressure plate could be the exact interaction needed to trigger a switch, maybe one that temporarily turns off gravity, like we discussed.
Ooh, nice.
Or you could use a variable, like we just talked about, track the number of times a physics object bounces off a specific wall. Once it hits, say, 3 bounces, maybe that unlocks the next part of the puzzle.
So the collision itself, or data about the collision, triggers the logic.
Exactly. And this is why getting those collision masks right is so important. The accuracy and the type of mask you choose directly impact how reliable and predictable these triggers are. In a puzzle game, you need predictable interactions for players to figure out solutions. If your collision mask is sloppy, the puzzle might not work consistently, leading to frustration.
So spend time getting those masks accurate from the start.
Definitely worth the effort. It prevents headaches down the road. #TAG IV. Advanced physics concepts for puzzle games.
All right, we've covered the basics of individual physics objects, how they interact via collisions, and how to script the logic. But what if we want to build something more elaborate? Like a swinging bridge made of planks, or a little physics-based vehicle, or a chain, or a really complex catapult. This sounds like it leads us to joints.
You read my mind. Joints are the next level. They truly unlock a whole new dimension of mechanical design within Construct 3's physics engine.
What exactly are joints in this context?
Joints allow you to connect multiple physics objects together in very specific ways. This enables you to build those elaborate, dynamic contraptions that react realistically as a whole unit to forces and other objects. Construct 3 provides several types, each with its own unique purpose for mechanical simulation.
Okay, what types are there?
First, probably the most common one you'll use is the revolute joint. It's often called a hinge joint.
Like a door hinge.
Exactly like a door hinge or a pin. It connects two physics objects so they can rotate freely around a single shared point. Think of a pendulum swinging or the arm of a catapult pivoting.
So they're stuck together at one point but can spin around it.
Precisely. The objects themselves can rotate independently, but their position relative to that single joint point is fixed. And when you create this joint, you specify an image point on one of the objects, a specific pixel coordinate as the exact connection point. It doesn't have to be the center. This gives you huge flexibility.
So I can hinge a plank near its end to make a lever.
Perfect example. That's exactly how you'd build the pivot for your lever or catapult arm. Allows it to swing freely around a fixed point on your base structure. There's also a variation called the limited revolute joint.
Limited? How so?
It does the same thing, but restricts the rotation to a specific angle range you define. Perfect for something like a bell clapper that should only swing back and forth within certain limits, or maybe a gate that only opens 90 degrees.
It's very useful. Okay, hinge joints. What else?
Next up, we have the distance joint. This one is interesting. It makes two physics objects behave as if they're connected by an invisible, rigid pole of a fixed length.
An invisible pole.
Yep. They will always maintain the exact same distance apart no matter how they move or rotate around their attachment points, like two ends of a solid rod. Again, you can specify image points on both objects to define exactly where this invisible pole connects them.
Okay, keeps them a set distance apart. What's it good for?
Well, the cool feature with the create distance joint action is that you can also set a damping ratio and a spring frequency.
Spring, so the pole isn't always rigid.
Exactly. Setting the spring frequency makes the connection act like a spring instead of a rigid pole. It dictates how fast it tries to oscillate or bounce back and forth if one end is disturbed. Like 4 hertz means it'll try to bounce 4 times per second.
And the damping ratio.
That controls how quickly those oscillations die down. A damping ratio of 0 means it oscillates forever, like a perfect spring in space. A ratio of 1 means it stops almost immediately, very stiff, like a car's shock absorber.
So you can make stretchy, bouncy connections, like ropes or chains.
Fantastic for creating things like ropes, simple chains, or maybe bouncy platforms connected by springs. But one important note, the pole, or spring itself, is invisible. The physics behavior doesn't draw it. If you want a visual representation, like seeing the chain links,
You have to draw that separately with sprites.
exactly. You'd need separate sprites, maybe chain links, and then use event logic to position and scale them correctly between the two jointed physics objects each frame. A bit more work, but doable.
Okay, distance joints, potentially springy. What's the last type?
Finally, there's the prismatic joint. This one restricts the movement of two connected physics objects along a specific axis, defined by an angle.
Like sliding on a rail.
Exactly like sliding on a rail. They can move back and forth along that defined line, but they can't move sideways off of it. Perfect for making pistons, elevators, or maybe a platform that can only slide horizontally or vertically.
Can you limit how far they slide?
Yes, you can enable limits to set a lower and upper boundary for movement along that axis. So your piston only extends so far, or your elevator stops at the top and bottom floors.
Nice.
And even cooler, you can enable a motor on a prismatic joint. This applies a continuous force along the allowed axis, pushing the connected objects in a specific direction automatically.
Ooh, for automated stuff. Like sliding doors or lifts.
Incredibly useful for automated sliding doors, hydraulic lifts, moving platforms that are part of your puzzle's mechanism. The creative potential for building intricate, interconnected mechanical puzzles using these three joint types, revolute, distance, and prismatic, is just massive. You could build incredibly complex Rube Goldberg machines entirely within Construct 3.
That's incredible. These joints open up so many possibilities for complex contraptions. Moving from the physical connections, let's think about behavior over time. How does Construct 3 help us manage complex behaviors? Things that functionally act like finite state machines, even if, it doesn't explicitly call them that in the interface. What does that mean for designing a puzzle game where maybe an object needs to do different things at different times?
That's a really crucial question for building any sophisticated game logic, especially in puzzles where elements might change function. And you're right, while Construct 3 doesn't typically present you with a formal FSM diagram tool or a visual state machine editor like some other engines might.
It doesn't have that specific feature.
Not in that visual diagram sense, no. But it absolutely provides all the powerful tools you need to implement state-driven logic very effectively. You can manage different phases or behaviors for your objects using that powerful combination we discussed. Event groups and sub-events, alongside variables or maybe object instance variables to track the current state. This is essentially laying the groundwork for how a finite state machine operates, just using Construct's existing event system.
Okay, so you build the states using event groups and variables. Can you give an example?
Sure, let's think about a specific physics puzzle piece, maybe an activation block. It needs to be pushed into a slot.
Okay.
It might start in an initial state. In your event sheet, you'd have an initial state group. The conditions and actions here might just make it sit passively, maybe waiting for a collision.
Right.
Then, once the player applies a force or an impulse to it, maybe a variable called block state gets set from initial to moving. This could activate a different event group, the moving state group. The logic here might handle its rolling physics, maybe check if it's near the target.
So the variable change switches which group is active.
Exactly. Or conditions within the groups check the variable. Then, once it reaches its destination and correctly settles into the target slot, maybe a collision trigger sets the block state variable to locked. This activates the lock state group.
And in the lock state,
The actions in the lock state group might make the block immovable using physics properties, play a puzzle-solved sound, and maybe trigger the next part of the puzzle. It no longer reacts to being pushed.
Ah, I see. So each state is basically a set of rules in an event group, and variables control which set of rules is currently running.
That's a great way to put it. Or think about an enemy AI in a game that involves physics puzzles. It could transition between states, patrolling, following a path, maybe avoiding physics obstacles, chasing, applying forces towards the player if detected, and attacking, maybe launching physics projectiles. Each state would be its own event group, with conditions checking things like player distance or line of sight, and actions controlling movement and attacks.
Or even a simple pressure plate.
Perfect example. A pressure plate could have an unpressed state and a pressed state. A physics object landing on it switches the state variable, which in turn activates or deactivates different event logic, maybe opening a door only while the pressed state is active.
So this modular approach, using groups and variables, lets you build state machines without needing a special diagram tool.
Precisely. It provides the practical means to implement complex, predictable, state-driven logic. It helps manage complexity, makes debugging easier because you can focus on one state's logic at a time, and ensures your puzzle elements behave in controlled, predictable ways, which is absolutely paramount when designing puzzles that require precise solutions. Your objects don't just react randomly, they behave purposefully according to their current mode or state.
Yeah.
Hashtag tag Tel Aviv. Optimizing your puzzle game and the iterative process.
All these physics simulations, joints, state machines. It sounds absolutely amazing for creating cool puzzles, but I keep coming back to performance. I imagine all this complex calculation could quickly become a bottleneck, right? What are the really crucial performance considerations we need to keep in mind to make sure our physics puzzle game runs smoothly, especially knowing physics is so CPU intensive?
You've hit on probably the most vital point for physics-heavy games. Yes, physics simulations are inherently very CPU intensive. All those complex mathematical calculations, figuring out collisions, applying forces, resolving joint constraints, they happen every single frame, and they add up fast. So optimizing your game isn't just nice to have, it's absolutely paramount for ensuring smooth, responsive gameplay, especially if you're thinking about targeting less powerful hardware like older PCs or mobile devices.
Okay, so what are the big hitters? What should we focus on?
All right, here are some actionable best practices, the main things to watch out for. First, and this is usually the biggest offender, avoid having too many active physics objects simultaneously.
Too many balls bouncing around.
Exactly. While Construct 3 and Box 2D are pretty efficient, having hundreds or even sometimes dozens of active physics objects all colliding and calculating forces every single frame will quickly overwhelm the CPU. This leads directly to slowdowns, low frame rates, stuttering gameplay. So design your puzzles thoughtfully. Try to limit the number of active physics elements the player needs to deal with at any single moment.
Okay, less is more for active physics objects. What else?
The engine does have that clever built-in optimization we mentioned, sleeping objects.
Right, when they stop moving, they stop using CPU.
Mostly, yes. Physics objects that come to a complete stop, zero velocity, zero angular velocity for a short time, are automatically put to sleep by the engine. When asleep, they consume virtually no CPU cycles until something disturbs them again, like another object hitting them or a force being applied. It's a great feature.
There's always a but.
The but is that even tiny, almost imperceptible movements can keep them awake. A tower that's still teetering ever so slightly, a ball vibrating minutely against a floor. These might not look like they're moving, but the engine might still be calculating for them. So if you need an object to truly stop consuming CPU, maybe once a puzzle piece is locked in place, you might consider explicitly setting its velocity and angular velocity to zero using actions, or even setting its physics behavior's enabled property to false.
Forcing it to sleep, essentially.
Kind of, yeah, just ensuring it's truly inactive. Now, this next one is a huge tip, especially for beginners, and it catches so many people out. Do not use animated sprites directly with the physics behavior.
Wait, why not? I want my bouncy ball to look like it's squashing.
You can still have the visual swash, but the problem is if an animation frame changes the size or shape of the sprite itself.
Like a squash and stretch animation does.
Yeah, exactly. When that happens, Construct 3 has to basically remove the old physics object associated with that sprite shape and then recreate a new one matching the new frame shape every single frame the animation changes.
That sounds bad.
It's terrible for physics. It's like constantly teleporting the object slightly. It causes instability, jittering, weird bounces, objects potentially falling through things, and it's a massive performance hit.
So how do you animate physics objects visually?
The absolute best practice is this. Use an invisible sprite that has the physics behavior applied to it. This invisible sprite should not have any animation that changes its size or shape. Keep its collision mask stable.
Okay, an invisible physics dummy.
Exactly. Then you take your actual animated sprite, the one with the cool squash animation, and you pin it to the invisible physics dummy using Construct's pin behavior.
Ah, so the physics happens on the stable invisible thing and the visuals just follow along.
Precisely. The physics calculations stay stable and efficient on the invisible object, while your visually appealing animated sprite simply gets positioned on top of it every frame. It's a game changer for combining animation and physics smoothly.
That's a golden tip right there. Okay, what else? Size matters?
Yes, be mindful of object sizes and stability. Box 2D, the engine, works best when objects aren't extremely small or extremely large or have really extreme proportions.
Like super tiny dots or huge walls.
Right. Objects generally under about 5 pixels wide or high, or maybe over 500 pixels, or things that are super thin, like 5 pixels wide but 500 pixels tall. These might not simulate realistically. They can lead to instability, unexpected behavior, sometimes even falling through each other more easily.
So keep things reasonably sized.
Aim to keep the widths and heights of your main physics objects generally within that 5 to 500 pixel range if possible. Physics simulations tend to be most stable and predictable when objects are of roughly similar sizes and masses, interacting at relatively low speeds. If you need tiny visual details, consider making them separate. Purely decorative, non-physics objects pinned to the main one.
Good rule of thumb. What about things going off screen?
Always good practice to destroy off-screen or invisible objects if they're no longer needed. Think about projectiles fired off into space, or maybe puzzle pieces that get discarded and won't come back.
Just let them fly away forever.
Not ideal. They might still be consuming resources. Use constructs destroy outside layout behavior, which automatically removes objects once they leave the visible screen area. Or if you might need them later but not right now, you could just set them to invisible 0% opacity and maybe disable their physics behavior.
Does invisible still use power?
Invisible objects still consume some GPU power just by being part of the scene, even if you can't see them. Destroying them completely is better for managing memory and freeing up both CPU, if physics was active, and GPU resources, especially important on mobile.
Okay, clean up after yourself. Anything on the event sheet side?
Yes, definitely event sheet optimization. Be really mindful of your event structure, particularly with things that run constantly. Avoid using the every tick condition for operations that absolutely do not need to run every single frame of the game.
Because that runs 60 times a second.
Or even more, depending on the frame rate, it consumes a lot of CPU. Ask yourself, does this check really need to happen constantly? Often the answer is no.
What's the alternative?
Use more specific triggers, use on collision, on button press, etc. If a condition only needs to fire once when it becomes true, use the trigger once while true condition. And consider disabling entire event groups when they are not needed. If you have complex AI logic, disable that group when the enemy is off-screen or inactive. Every little bit helps save processing power. ##B, the power of prototyping and rapid iteration.
That's a treasure trove of advice for keeping things running smoothly. But beyond just performance, what about the actual process of developing the game? I keep hearing that Construct 3 is absolutely amazing for rapid prototyping. How does that help specifically when making a puzzle game, where tweaking is probably constant?
Oh, it's huge. This is genuinely one of Construct 3's biggest strengths, and it's a massive advantage over many traditional coding environments, especially for puzzle design. Its capability for rapid prototyping is simply exceptional.
Why is it so good for that?
Think about how puzzle design works. It's inherently an iterative process, right? You have an idea for a mechanic, you build a quick version, you play test it immediately. You see what works, what feels good, what's frustrating, what's too easy or too hard. Then you tweak it, test again, tweak again.
Constant refinement.
Exactly. Construct 3 facilitates this loop incredibly well. Features like the simple preview button are key. You click it, and boom, your game is running instantly in your web browser. There are no long compilation delays like you often get in other engines, which can really break your flow.
Instant testing.
Nice.
Even more powerful is live editing. This is amazing. While your game preview is running in one browser tab, you can switch back to the Construct 3 editor tab, make changes, maybe tweak a physics property like friction, adjust a variable controlling jump height, move a platform slightly, and then switch back to the preview, and you'll often see the impact of your change immediately without even needing to restart the game.
Wow, real-time changes.
Often, yes. This immediate feedback loop is just invaluable for puzzle design. It means you can. What? Like, test ideas faster.
Super fast. Quickly test new ideas for mechanics. Adjust difficulty on the fly, make that ramp a tiny bit steeper, make the ball slightly less bouncy, make the target area smaller, and see how it feels instantly.
Fine-tune the feel.
Exactly. Refine those interactions until they feel just right, until they provide that satisfying aha moment you're aiming for. Experiment with different physics values until that chain reaction behaves exactly like you envisioned it.
So it encourages experimentation.
It absolutely encourages constant iteration and refinement. It reinforces the mindset that game development is an iterative journey. You shouldn't be afraid to experiment, try weird ideas, test constantly, see how small changes affect the feel, the challenge, the performance. It's how you discover what truly makes a puzzle fun, engaging, and fair. You can fail fast with a bad idea and pivot quickly to try something better. It drastically speeds up finding the fun. Hashtag tag outro.
Wow, what an incredible deep dive this has been. Seriously packed with information. We've really covered a lot of ground today, haven't we?
We definitely have. It's been a comprehensive journey.
We started with understanding Construct 3's whole intuitive no-code approach, setting up that first 2D scene with layouts and layers.
Getting familiar with the workbench.
Then we plunged right into the heart of it, harnessing that powerful Box 2D physics engine. We dissected how to fine-tune all those crucial properties: density, friction, elasticity.
Getting the feel just right. And learning how to manipulate objects dynamically using forces and impulses in a physics-friendly way.
And we didn't forget structure. We saw how graphic layers are critical for organizing visuals, managing drawing order, and even impacting performance.
Then we explored the brain, the event sheet, mastering that visual, event-driven design with conditions, actions, groups, functions, and variables to build complex logic and even mimic those finite state machines.
But we even got into the advanced stuff. Seeing how physics joints, hinges, distance joints, prismatic joints let you engineer really intricate mechanical contraptions.
Opening up whole new puzzle possibilities.
And finally, wrapping it all up with those vital optimization techniques to keep our physics games running smoothly, and emphasizing that amazing power of rapid prototyping and iteration that Construct 3 offers.
It really provides a solid foundation covering the core tools and concepts you need to get started.
Absolutely. So now, the most exciting question, the one we always like to end on, is really for you, the listener.
Yeah, thinking about everything we've discussed, armed with these insights into Construct 3's physics engine, its event system, the joints, the workflow, what kind of clever, challenging, maybe completely unique 2D physics puzzles will you now engineer and bring to life?
That's the challenge. Thank you so much for joining us for this deep dive into the fascinating world of creating 2D physics puzzle games with Construct 3. We really hope you feel incredibly well informed.
And more importantly, inspired and ready to start building something awesome.